Welcome back to Introduction to Statistics. Today we're talking about the one sample t-test. And with each test, we're going to keep using these 6 steps as we walk through it. So we're going to state the hypothesis, select the statistical test, check the assumptions, set the criteria, compute the test statistic, and then make a decision. So when we state a hypothesis for a one sample t-test, it's going to be very similar to a one sample z-test, where we have the alternative and the null. In this case, Dr. Rasko thinks students at WT will have higher SAT scores than the national average. That's the same general hypothesis that we had for the one sample t. The alternative and the null are mutually exclusive. They're inclusive of all possibilities. We talked about that more in the previous video. The only thing that's really different is we don't have sigma anymore. You see that I've crossed it out. Just that simple change, that one little tweak, shifts you from one sample z-test to a one sample t. If we don't have a measure of variability, either the standard deviation or variance from the population, we will have to do a one sample t-test instead of a one sample z-test. Now we still need the mean for the sample, we still need the mean for the population, we still need some measure of variability from the sample, either the standard deviation or the variance. So we do need those things, but the only real difference is, do we have that source of variability from the population? Now I've crossed it out, basically pretend like it's not there. I'm trying to highlight the fact that that's really the only difference between these two things is what source of variability are we using for our calculations. So when you walk through these charts, you can see that we are doing a comparison. We're comparing a sample to a population, right? If you look at this bottom row, we see that population to a sample with a one sample z-test, it indicates that sigma or sigma squared, so standard deviation or variance from the population, is known. Next to it, we see population to a sample, but sigma squared is not known, and standard deviation or the variance for the sample is known. So again, we still need those pieces of information, or we need to be able to calculate them. And if I give you the sample data, you can calculate the mean and standard deviation for a sample. So we still need those pieces of information, but we don't need this population, variance, or standard deviation anymore. Now, this chart also walks through it the same way. So we're going to walk through it just like we did in the last video. So Dr. Rasko thinks students at WT have SAT scores that are higher than the national average. We're comparing groups. In particular, we're comparing a population to a sample. Thus, when we look at how many groups are we comparing, how many samples, we really only have one sample, and then we have a population that we're comparing to. So our sample mean is 532, standard deviation is 21.2, and that then tells us that we're in this first group. So it's either a one sample Z or a one sample T, and as we've already indicated, we have crossed out, we no longer have the sigma information, we don't have a variability for the population. Because of that, we do a one sample t-test instead of the one sample z. Now, if I could do both, like we saw in the last video, one sample t-test I mentioned has more power, all things being equal, and we'll talk more about why that is in this video, but all things being equal, one sample z-test has more power, you're better able to find a difference, assuming one exists in the population. Because of that, we would do a one sample Z if we could do both. And in fact, in the last video, you had all the information. You could have done a one sample T. We did a one sample Z though, because when you could do either of them, one sample Z test is preferred. So what we're going to do now is substitute the standard deviation, or if we had the variance for the sample, we're going to substitute that variability in place of the variability from the population. Now, as we've mentioned, a lot of the time samples don't have the same amount of variability as the population. We have to do things like divide by n-1 to account for that when we create our error estimates. However, we're going to use that to approximate the variability that we would expect to see in the population, because that's the only variability estimate that we have. When we look at assumptions, as I mentioned in the last video, the assumptions for one sample z-test and one sample t-test are identical. So we still need normality. We need that normal distribution, in particular normal distribution for the error, but you can look at the original scores and see. We also need random sampling and we need independence. And as we talked about in the last video, this simpler version of the question that is initially provided really doesn't address random sampling and independence. Now, normality, we have to check that statistically. We have to draw a histogram. We can also do skewness, kurtosis. There's other ways of quantitatively measuring it. We're not going to focus as much on the quantitative measures for this class. I don't know that you want to do a one sample Kolmogorov-Smirnov test or even try to pronounce Kolmogorov-Smirnov test. I stumble over it on occasion. And so because of that, we're going to focus on just the histogram for normality. What we also are going to do, though, is random sampling and independence. You can really look at those conceptually from the research design, because when we add in some details and let you know, yeah, in fact, Dr. Asko knew what he was doing. He randomly selected 100 WT students. Well, now, from that phrase, I know that, in fact, we do have a random sample representing those 100 WT students. Because if I don't know that it's random, it's possible that it's biased in some way. And even if it is random, it's still possible that it doesn't fully represent, but odds are that it will represent WT students, assuming that it's truly random. Additionally, we see things like individually. That lets us know that the scores should be relatively independent of each other, with the exception of the fact that they all are WT students. However, that's really our variable of interest. Thus, the fact that they're connected on that doesn't violate the independence. Other than their association with WT, they should all be independent of each other. And if we're testing them individually, making sure that they can copy off of each other, work together, any of those things, we should have independence. Now, the next step is setting the criteria. And here you can see the Z distribution versus the T distribution. In fact, there's multiple T distributions depending on the degrees of freedom, and we'll talk more about that here in a moment. But this provides you 3 examples where we have the Z distribution and then we have T distributions when your degrees of freedom is 1, 5, and 20. And you can see as degrees of freedom increases, then you get closer and closer and closer to the Z distribution. However, we do pay a price, especially when we have very limited degrees of freedom, which are related to the sample size. So as we have a larger sample, we will better approximate the population. Our distribution will get closer and closer to the Z distribution, which is based on the population. So the basic idea is that when we look at the area under the curve, here I've indicated about where 1.96 is, that would give us 2.5% of the area under the curve. So if we're doing alpha is 0.05 and we are splitting it, so it's a 2-tail test, our cutoff, our critical value for Z is 1.96 under those circumstances. However, when we do the same amount of area for a T distribution, what you see is because there's more distance, more area between the baseline of 0 and the curve, we're going to need a smaller amount of area lengthwise. So if you think about a room, if I wanted to have enough room for 10 square feet, well, if I have a room that is relatively deep, I don't need the room to be as wide in order to get to 10 square feet. By contrast, if I have a room that's relatively shallow, I'll need the room to be wider to accomplish the same amount of square feet. So basically that's the same idea here, where if I have more height between the axis and the curve, then what's going to ultimately happen is I need less width to accomplish the same amount of area to get that 2.5% of the area under the curve. So what that ends up doing is before, again, if we were doing a 2-tailed Z-test with an alpha of 0.05, we end up with positive 1.96, negative 1.96, and you can go to the table to double check that, the Z critical table. When I do a t-test with the same basic ideas, I end up with positive 2.09 and negative 2.09. Now, what this means is to have a significant difference, I'm going to need to pass that larger critical value. So now instead of needing to be larger than, greater than, more extreme, rarer than 1.96, I need to be more extreme, rarer than 2.09. And in case you're wondering, where are these numbers coming from? Well, we can compare the Z critical and the T critical charts. So you've seen critical values for Z before, and that's in the formula sheet. We have a similar chart for critical values of T. And really where these are coming from is somebody has graciously done the math for you to determine the area under the curve and then the point at which we have 2.5% of the area or 5% of the area under that curve based on the alpha that we desire. You can see that these are very similar. And in fact, if you look, when degrees of freedom is infinite, which would basically be a population, not surprisingly, the values for T critical are going to be identical to the values of Z critical. So suddenly, if alpha is 0.05 and we're doing 1/10, the cutoff is 1.65 for Z and for T. If alpha is 0.05 and it's 2/10, the cutoff for that is 1.96, whether you're using Z or T. The difference is with a t-test, we really don't ever reach infinity, because if we did that, we might as well just call it a z-test, because we have the entirety of the population if we've reached an infinite number. You can also see, if you look at this, that the cutoff value, the T critical, is going to get larger and larger and larger as degrees of freedom get smaller and smaller and smaller. So in case you're wondering where this came from, if you look in your textbook, Appendix C, Table D, which is on page 388, if you look at the actual book, in the electronic book, I think it's similar, but you can always look for Appendix C, Table D, and you will find a table very similar to this. It is a little bit different in the sense that I've cut out some of the numbers here and there to simplify it so I can present it more effectively in a PowerPoint, but the values should be identical. I think he goes to 3 decimal places. I've also rounded a little bit here and there. So you know how to basically do the alpha level. You know how to determine if it's 1/10 or 2/10, whether it's directional or non-directional, based on the previous video. The part that is new to using the critical value of T table is the degrees of freedom. And for a 1 sample T, degrees of freedom is going to be equal to n minus 1. So we have 100 individuals, if you remember, right? 100 people representing the number of individuals from WT. We're going to subtract 1, thus our degrees of freedom is going to be 99. Basically what it is we have to pay a price for the fact that we need to calculate means and things like that for this sample. So the last individual, if I know that my mean has to be 532, every person up until the 100th person, their mean can be whatever. But if I know that the mean for the group has to be 532, that last person is not free to vary. We could, by a process of deduction, decide, well, I've done all the calculations. I know that to make the average be 532, the last person's score has to be X, right? Whatever that is. And so it's basically the process of algebra. Well, that means that that last person's score is not truly free to vary if I need to constrain it such that it gets the mean that it is supposed to have for the group. So I'm not going to ask you a lot about that, but conceptually, that's where degrees of freedom comes from. That's why we subtract 1, is because that last person's score really is not free to vary. So when we're walking through this, we still have alpha is 0.05. We need that. We still need to know that our hypothesis is directional. Again, we've seen that in the previous video. What is new, and I've simplified the chart to make it fit, is once I know alpha is 0.05, once I know that it's directional or it's 1/10, well, the degrees of freedom is 99. So now my critical value is technically somewhere between 1.67 and 1.66. And I could in fact go to a table that has more values that tells me the exact value for degrees of freedom 99. In practice, especially within the class, a lot of the times we are using simplified charts. Well, you then have to decide, do I want to use 1.66 or 1.67? You should use 1.67. Again, the true value, 99 degrees of freedom, is somewhere between there. If it is significant at that level, it's significant at whatever it really is. Now, if the score, the obtained value, is between 1.67 and 1.66, that is where I would actually go and I would find a table that's more precise. That rarely happens. I don't know that in my entire career I've ever had it happen. However, it could happen where the value is right in between those two numbers. So how do we get the t obtained? Well, you've already seen us calculate z obtained, where we take the effect, which is basically in a one sample test, the difference between the sample and the population. We then divide that by our error term, the standard error of the mean. The standard error of the mean is coming from the variability in the population divided by the square root of n. We're going to do that same basic process for t, except we're using a different source of variability because we don't know sigma anymore. We don't know that it's 22.1. We are ignorant of that. We can't find that out because we don't have the data or we don't have that available to us. Well, with the t, we still have the same effect. It's the mean of the sample minus the mean of the population. It's still 532 minus 528. We're going to use a different standard error of the mean. You can see that we have represented that with SD with a subscript m to represent that is the standard error of the mean from the sample instead of the standard error of the mean from the population. Now, how do we go about calculating that? The standard error of the mean is simply going to be the standard deviation divided by the square root of n, or the variance from the sample divided by n, and we take the square root of the whole thing. So formula-wise, you can see if you look left to right, basically it's the same formula. The only difference is where is that variability coming from? Now the variability is coming from the sample, not the population. We're then going to put that 2.12 in here and we'll calculate t obtained. So in this case, t obtained is 1.8868. Very, very similar. The only thing we have to do is remember that our source of variability is now the sample, not the population. So we've talked about the standard error of the mean a couple of times, and you may at this point be wondering, okay, now I know how to calculate, but what is it really? Well, the standard error of the mean is the estimate of variability within the sampling distribution. So in a previous video, we talked about sampling and the sampling distribution. And we talked about how for any sample or any population, you can pull a sample from it, calculate a mean for that sample, and you could do that for all possible samples. And we talked about how if you look here and where it's highlighted in blue, if I did that for even something as small as the population that we used with only 10 scores, if I pulled all samples of size 5 from those 10 scores with replacement, we end up with 100,000 possible samples, right? And we have to then compute a mean for all of them. I mentioned in that video, you don't want to do that. I don't want to do that. Well, this standard error of the mean estimate is basically making it so we don't have to do that. So what that represents is if I did do that for all 100,000 possible samples and I computed a mean for them, I can then create this sampling distribution that you see on the right, where I have all the possible means. And again, this only shows 64. Really, we would need to do this 100,000 times. But I have all possible means. And then I'm interested about the variability within those. So what we're getting at is sampling error. So every sample is going to be a little bit off of the population mean, right? We're trying to quantify that. So in our original data, when we're doing a sample and we're looking at variability within the sample, we're saying how far is each score from the mean of that sample, or even a population? How far is each person's score in that population from the population mean? Well, if we get the average deviations, right, the average variability of each score around the mean, we end up with the standard deviation. The standard error of the mean is basically that same thing, but with the sampling distribution. So now we're saying, how far is each sample mean from the grand mean? How much does each sample mean vary around the grand mean, deviate around the grand mean? Basically, what we're saying is the sampling error, we want to quantify it. We want to know how much average error there is in each of these samples around the grand mean or around the population mean. And this then provides us with an estimate of that without having to generate 100,000 samples and calculate a mean for each one. And if you know how to code, you can do it. The computer can do it within a few minutes, but it saves us a lot of hassle. And historically, it was not so easy. When this all started, they had to do it by hand, basically. I wouldn't want to sign up for that. I'm really glad I was not a grad student during that time. What this allows us to do, this standard error of the mean, this SDM that we see, is providing us with an estimate of that. And if we actually did this, you would find that this estimate and the actual standard deviations within the sampling distribution would be slightly different. That being said, it's a small difference, and I am glad that we don't have to do it. And so that's really what this is trying to tell us. The standard error of the mean is basically telling us about the average deviation of each sample mean around the theoretical population mean or the grand mean of all the samples. So we now have the critical value. We also have the obtained value, and similar to before, what we're going to ask is the obtained value more extreme? Is it rarer? Is it less likely, less probable than the critical value? As we talked about in the last video, the critical value could be positive or negative because it's a one-tailed test, a directional test. We already know that it's positive because we're anticipating that the sample mean will be greater than the population mean. If that is true, it should turn out that it's positive. So we have the t-distribution. It's similar to the z-distribution, still centers around 0. We have our cutoff or our critical value of positive 1.67. Our obtained value, rounding to 2 decimal places, is 1.89. And so because of that, we know that we have rejected the null. It does seem that, in fact, WT students are performing better on average than the national average because 1.89 is more extreme, rarer, less likely than positive 1.67. We can calculate an effect size for the t-test. We can still use Cohen's d for the one sample t. And when we look at this, it's the same formula as Cohen's d for a z, except we now use standard deviation from the sample instead of standard deviation from the population because standard deviation from the population is not known. So basically this denominator here, we're switching from sigma to SD. We're switching from the population standard deviation to the sample standard deviation, and the rest of it stays the same. We can then use t-critical and the standard error of the mean to calculate a confidence interval. And you've seen this before, but we did it in the practice video for Excel. The idea with the upper and lower limit is if I sampled again, right, thinking about the sampling distribution, every sample is going to be a little quirky. It's going to have that person that's a little bit off. It's going to, right? And so most of them aren't going to hit right at the population mean. If we sampled again, it wouldn't be that the mean for the new sample would be exactly 532. We want to know, assuming that our original sample mean is representative of the population, where would we expect the means to fall if we sampled again, if we got a new sample? Well, if we got a new sample, we would expect that the mean for the new sample would fall somewhere between 535.5404 and 528.4596. So what we're doing is quantifying the variability. So variability in the sampling distribution, again, is quantified with the standard error of the mean. So we're saying, okay, we have the standard error of the mean. We want to know within some level of probability, which is represented by t critical, where are the means going to vary? How are they going to vary around this mean that we already have obtained? And thus we can quantify it. Now, as a note, here I always use upper limit and lower limit, where upper limit we add t critical times standard error of the mean, lower limit we subtract t critical times standard error of the mean. This assumes that t critical is positive. It is possible if you had a negative t critical because you had a directional test that went in the negative direction, you expected the sample would do more poorly compared to the population, it would be such that you would need to flip these. However, if you just always use the absolute value of t critical or z critical in these calculations, it will always be that the upper limit you add, the lower limit you subtract. So again, t critical, z critical can be positive, they can be negative. If we're doing a non-directional test, they are positive and negative. But if you just always use the absolute value, if you always assume that t critical or z critical is positive, it will always be that your upper limit you add t critical times the standard error of the mean, and with the lower limit you subtract t critical times the standard error of the mean. So then how do we go about reporting this? Reporting is very similar. So students at West Texas A&M University, N is 100, mean is 532, standard deviation is 21.2, performed better on the SAT than the national average, mu 528, T 99, that's the degrees of freedom, is equal to 1.89. Here I've rounded to 2 decimal places because typically when reporting, we report to 2 decimal places. Occasionally we will report to 3 for different types of tests. For this class, 2 should be fine. P, and we've talked about that before, P is less than 0.05. Because we rejected our null, we know that P has to be less than our alpha. And in the video on SPSS, I'll show you how to get an exact P value. But for the moment, we know that P, the probability of our obtained T, has to be less than alpha because our obtained T was more extreme, less likely, less probable than our critical value, than our cutoff. And then we have Cohen's D, which when we round is 0.19. The only part that's really new, one, we added the degrees of freedom. Because we added degrees of freedom and degrees of freedom go in parentheses, I've removed the parentheses around mu and the t-test. So if you look at the other video, it was open parentheses, mu equals 528, z-test, and then at the end, after Cohen's D, I did a closed parentheses. However, you want to avoid parentheses within parentheses. Because of that, I've used a colon, given the information, and then done the degrees of freedom in parentheses. The other part that's new is you'll see that I have added the confidence interval around the mean. So we have a mean of 532. In brackets, we then have the confidence interval, and I could put 95% confidence interval, 95% CI in front of the brackets, and in fact, probably that would technically be more correct. But we have the confidence interval in brackets 528.46 to 535.54. So our lower limit, comma, upper limit within those brackets. And the visual would actually be identical. We're just showing the mean. Now we could put confidence intervals or some type of variability interval estimate around these, and we could add to that. Again, for the purposes of this class, we're not going to go into adding the lower and upper limits to these visualizations.